This is the second page of the parametric equation notes. This example 2 here follows directly from the worksheet, the introductory worksheet, where you graph some ellipses and hyperbolas in parametric form. And you hopefully will recognize that this first equation is an ellipse in polar form, in parametric form, and this one is a hyperbola. Now, if I tried to put this into if I tried to eliminate the parameter t to put this in rectangular form by solving for t, if you look at this first equation, what I would end up having is x minus 1 divided by 3 equals cosine of t, and t would be equal to inverse cosine of the quantity x minus 1 over 3. And the second equation would be t is equal to inverse sine of the quantity y plus 1 over 2. I think I meant to say x minus 1 over 3 on the first one, not t. But anyway, I would have an inverse sine of a algebraic expression equal to an inverse cosine of an algebraic expression, and there would be absolutely no way to figure out how to make that look nice. So that's not the way we do it with this particular type of function. What we're going to do is, instead of isolating t, we're going to isolate the trig functions. So the first equation, if I subtracted 1 from both sides, x minus 1 would equal 3 cosine t, then divide by 3, that would equal cosine of t. The second one is y plus 1 divided by 2 is equal to sine of t. So that would be the second equation. Now, recall a trig property. We know we have a trig property that says cosine squared of theta plus sine squared of theta equals 1. Only I'm going to write cosine squared of t plus sine squared of t equals 1, because it doesn't matter what I call that angle, and I want to use t in this case. Now, what I can do now is, looking over here, I have a cosine t. I'm going to make this cosine squared of t, and I'm going to square the other side of the equation. Then I have sine of t. I'm going to make that sine squared of t, and I'm going to square the other side of the equation. So now what I can do is I can substitute x minus 1 over 3 in for cosine t, and y plus 2 over, or y plus 1 over t 2 squared in for sine squared of t. And so I end up with this, x minus 1 over 2, or so over 3. I'm not talking well today, sorry. X minus 1 over 3 squared substitutes for cosine squared of t, plus y plus 1 over 2 squared, which substitutes in for sine squared of t, equals 1. And there's the equation of the ellipse. I can, to write it the way you're more used to seeing it, this would be x minus 1 squared over 9 plus y plus 1 squared over 4 is equal to 1. So there's my equation. You'll notice, remember that when we looked at the worksheet, sine and cosine could switch places, and it didn't make any difference in what the graph looked like. That's because I could also have written this sine squared t plus cosine squared t equals 1. I could have substituted these, the x minus 1 over 3 squared in for the sine squared and the y plus 1 squared in for the cosine squared. It doesn't make any difference since we're just adding those two terms. So it really doesn't matter whether I put cosine or sine here and here. Now, hyperbola, we have secant and tangent instead of sine and cosine. So if I'm going to go ahead and solve for secant and for tangent. So I have, on the first one, it would be x minus 2 divided by 3 is equal to secant of t. And the second one would be y minus 4 divided by 5 is equal to tangent of t. And once again, if I, well, I won't square both sides yet because you don't know what I'm trying to do with this. There's a property that involves secant squared and tangent squared. Actually, I'll go ahead and square it because you know that I'm going to have to do that since I just said so. I'll square both of these. There is a property that involves secant squared and tangent squared, and the property is this: 1 plus tangent squared, and I'll use t, equals secant squared of t. Or I can say 1 equals secant squared of t minus tangent squared of t. So now what I'm going to do is I'm going to substitute the y minus 4 over 5 squared in for tangent squared of t, and the x minus 1 over 3 squared in for secant squared of t, and I'll have the equation of a hyperbola because we're subtracting now. So 1 is equal to x minus 1 over 3 squared minus y minus 4 over 5 squared, and that gives me, if I put the 1 on the other side and made it look more familiar, x minus 1 squared over 3, or sorry, over 9, minus y minus 4 squared over 25 equals 1. So there is the equation for a hyperbola. Now notice it's secant squared minus tangent squared. This is the positive term. That's why it opens in the direction of the secant term, and why we can't reverse those. If we switch secant and tangent here, then that means that the variable, the expression involving y would be the positive one, and then it would open in the y direction instead of the x direction. So the order does make a difference with the hyperbola. Now, writing parametric equations. What we've done so far is we've had a parametric equation, and we figured out a way to eliminate the t and write it in xy form, or in rectangular form. But if I start out in rectangular form and I want to write parametric form, and I have an equation already, the only thing I need to do is split up the variables so that I have x's on one side, y's on the other, and then set each side equal to t. Now, there's more than one way to do this. So for example, I could say 3x is equal to 24 minus 4, or sorry, yeah, 24 minus 4y. And I could set each side equal to t and say 3x equals t and 24 minus 4y equals t. Since they're equal to each other, they're both equal to another variable t. And then I would just have x equals t divided by 3. And here I would have negative 4y is equal to t minus 24, or y is equal to negative 4t plus, no, I got to divide by negative 4. Negative t divided by 4 plus 6. Negative 24 divided by 4. So that would be one way. Now, that's not the only way, because I could also say, what if I got x on the other side? And I would say 4y is equal to 24 minus 3x. I would get a different set of parametric equations. I would get t is equal to 4y, and t is equal to 24 minus 3x. And then I could say, actually I'd rather write them the other way around. Sorry to mess you up. I know you hate it when I do that. I could say 4y, because I want to end up with x and y on the left, so I'm just going to do 4y equals t, 24 minus 3x equals t. So here I would have y equals t over 4, and here I would have, if I subtract 24 and divide by negative 3, I would end up with, I'll just go ahead and do it in 2 steps. Negative 3x equals t minus 24, or x is equal to negative t over 3 plus 8. 2 different parametric equations, but you'll find if you put them in the calculator, you get the same figure. Now, what's going to happen is the time, or the underlying t variable, is going to not match up the same way with x and y in both equations, but it's the same variable. And these are not the only 2 ways I could do this. I could also solve the equation for y, for example, or solve it for x, and then just say x equals t or y equals t, and then the other variable equals everything else. So there's a lot of different ways to do this, but so there is not one unique parametric way to write parametric equations. So that's the moral of the story. Okay, in conic form now, once again, we're going to kind of reverse what we did up above, and we're going to say this is in the form cosine squared t plus sine squared t is equal to 1, and then I'm going to just say x minus 3 squared over 25 is equal to cosine squared of t. Take the square root of both sides of that, and I end up with x minus 3 over 5 is equal to cosine of t. So x minus 3 is equal to 5 cosine of t. X is equal to 3 plus 5 cosine of t. So there's, that's what we ended up with. That's how we started before. This is how we get back to that. Then I do the same thing with the sine. I say y plus 7 squared over 16 is equal to sine squared of t. I take the square root of both sides. I end up with y plus 7 over 4 is equal to sine of t. And some of you may be asking me about the positive and negative. Basically, since I have positive and negative on both sides, and y can vary, it turns out I basically get all the values that I need just by doing this. I don't need to actually write positive and negative on both sides. Y plus 7 is equal to 4 sine of t, or y is equal to negative 7 plus 4 sine of t. So there's my parametric equations for that ellipse. And then if you had a hyperbola, you'd do the same thing, only you'd do secant squared t minus tangent squared t equals 1. Now, using parametric functions to explore inverses, the idea here is if I have an equation, say y equals 4 sine of x. Okay, and so I graph this, and I want to, if I graph this, I'm going to get an equation that looks something like, it's going to go up and down and up and down and so forth. Actually, I'm going to draw it so I can see more of both sides. I'm going to get a sine function. It's going to go up and down. It has an amplitude of 4, so it's going to go up to 4, and it's going to go down to negative 4, and it's going to go back and forth, so something like this. If I wanted to put this in the form of parametric equations, I could just say x equals t and y equals 4 sine of t. Basically just saying that, and this is something I can always do to write parametric equations, because if x equals t, then basically I'm substituting the t in here for x. So y is just 4 sine of t. So if you have an equation that's just solved for y, you can always do that. Just say x equals t, and then y equals the equation, but with t in it instead of x. And if I graph this as parametric functions on the calculator, this is what I'll get. Now what I want you to do is see what happens when I switch these around. What if I do y, or x equals 4 sine of t and y equals t? What happens when I completely switch these equations, when I switch what's inside? Actually, I didn't switch the x and the y. What I switched was what they equal. So if I switch these two and write it like that, what happens? Well, it turns out, actually let me pause and I'll do it on the calculator, and then I'll come back and show you. Okay, if you look at the graph here, this is the original equation, x equals t, y equals 4 sine of t. I did have to make an adjustment. If you go to tab and let me up arrow a couple times to my equation, notice that the t step, this was 0 to 6.28, which only gave me one cycle of the graph. It only gave me this first sine cycle from here to here. If I wanted to see the graph go all the way across the screen, that's why I did the negative 10 to 10, because that's what's showing on this. I could have done any number, but since my screen was said negative 10 to 10, I just used that. Now, let's compare that now to when I switch the x and the y rules here. When I say x equals 4 sine of t and y equals t, notice I get a graph that is not a function, but is the inverse of the original function. So basically x and y have switched places, so this gives me the inverse. Remember when we did in rectangular form, I could only get a piece of the graph from negative 90 to 90, or negative pi over 2 to pi over 2. But this allows me to see the entire inverse graph in parametric form. So just to draw this on here, basically what we're seeing now is we're getting to see the entire inverse graph. So you might want to write that down in your notes. Okay, that's the end of page 2. Check out another video for page 3.